beautiful black body. And that's the prediction of the Big Bang. The temperature is perfect, 2.7 Kelvin. And that's exciting. It tells you that it's very strong evidence that we got. I mean, this thing is about 25 years ago, but the original measurement is 1965. So since about the mid-1960s, there's been strong evidence that the Big Bang is the right model. There's a problem, though. The problem is that this picture that the universe is perfectly homogeneous, it's very uniform at very early times. If you look at the universe today, the universe is not homogeneous. I mean, we have galaxies all over the place. People in this room, it's obviously not homogeneous. So how did the universe go from being perfectly homogeneous to being completely inhomogeneous, to being full of galaxies? And that's a difficult question to answer, so it seems. And it turns out, in the context of the Big Bang, it's a very simple question to answer, it turns out. But there's a prediction also. The prediction is that if the universe was perfectly homogeneous, completely perfectly homogeneous, you could not produce galaxies today. The universe has to be very slightly inhomogeneous, very slightly, very small amount. And you can predict how much it must be inhomogeneous by. That was done also in 1970. You can make predictions about that the universe has to be almost perfectly homogeneous, almost perfectly uniform, but not perfectly. And 25 years ago, the idea is that if the universe is not perfectly homogeneous, this microwave background, this microwave background that you see, because the universe is not perfectly homogeneous, the microwave background will not be perfectly homogeneous. So I will measure a temperature of 2.7 Kelvin here, and a very slightly different temperature here, and here, and here. It will be on the average 2.7 Kelvin, but there will be small differences, very small differences. If these differences are not seen, you can't form galaxies today. They have to be seen. And that's the prediction. And the beauty is that for the last 20 years or so, people have been trying to find these small inhomogeneities. The first time they were found was by the Kobe satellite. And that is from a new satellite called the Planck satellite, which was released this year. And this shows the sky in the microwave background. So what's been done over here is that this 2.7 degrees Kelvin has been removed. So there's a uniform 2.7 degrees Kelvin on this. That's been subtracted. And what's left over here are these red and blue things. So if the sky were perfectly homogeneous, you would see a perfect blue or red thing. The fact that you see differences is telling you it's not perfectly homogeneous. What is even more beautiful is that you can actually measure these amounts. So these are at the millikelvin level. 0.2 millikelvin is the bluest point over here is 0.2 millikelvin, and the reddest point over here is plus 0.2 millikelvin. So the microwave background is homogeneous to 1 part in 10,000. Because this is 0.2 millikelvin and the temperature is about 2.7 Kelvin. So what you know, again, this is evidence, direct evidence, that the universe started off as being nearly perfectly homogeneous, but not perfectly homogeneous. Again, a prediction of the Big Bang. It has to be nearly perfect. And we'll come to why nearly perfect is relevant.
宇宙的那个温度现在低到说它的辐射啊，主要是在微波的波段，那个波段在地面上不太容易观测，所以都要放人造卫星去做。那左边那个是比较早年的观测，不过他的意思是这样，就是说我到了随着不同的波长啊，它的辐射的强度啊，跟一个完美的辐射体是一样的。一个热的灯泡，它就是一个完美的辐射体。那像那样子，它当然是解释说这些观测的资料点，那些点跟理论上物理算出来的那个辐射的那个曲线啊，是完美的那个符合，所以宇宙是一个很完美的辐射体。它温度呢，现在整个宇宙的平均温度就是2.725。可是它的那个望远镜啊，还有一个实验就是看不同的部分， 那每一部分我们都可以去做一个温度的计算，对不对？看这个地方的温度跟这个地方温度有没有差别？那这张图啊很重要，因为大家常常在杂志上会看到，就是它把各个地方量到的温度扣掉一个平均值，扣掉那个2.725这个平均值，还要扣掉很多，扣掉我们地球在这里面跑啊，扣掉银河系啊，扣掉太阳系，全部扣掉以后，就剩下来的是宇宙当时光变成透明了以后，当时的温度的高低起伏，其实就是密度，就是东西的分布。如果宇宙当时是完美的、很平整的话，就不会变成我们现在这么不平整的。有的地方有很多有星系、有物质、有光线、有你有我，这边有空地，不会。所以宇宙是真正看到当时的不完整、不平整的这个程度，是每10000分之一这样子的高低起伏，是这样子的小小的高低起伏，后来造就了宇宙的结构。
So as I said, the CMA anisotropy was first detected with the COBE satellite. After that, there were a number of other missions. There was the WMAP satellite about 15 years ago, and then Planck, this Planck satellite now. And today, you can do really detailed modeling of these anisotropies, these small inhomogeneities in the microwave background. And this gives you outstanding constraints on the cosmological model. I'm going to just show you a plot over here. I won't explain it, but this is a plot which basically tries to take these data and parameterize them. And another thing I should mention is that the shapes of these peaks, or the fact that are these peaks, is actually predicted in 1970. So it was predicted by Zeldovich and Peebles independently. So these are called acoustic peaks, and they come because of coupling between photons and baryons at this period. And we can talk about that too. I mean, it's a highly technical subject. But you can see that these are the data, and this is the best fit cosmological model today. So it's a wonderful fit of the model to the data. And this fit, is telling us that the universe contains about 30% of dark matter, 70% of dark energy. Okay, so how did we start off? We started off by saying that the universe was nice and homogeneous at the epoch of recombination. And then we reached galaxies. How did that happen? It happened because of these small inhomogeneities. And the idea is that if you have a region which has a little bit of higher density, and then you have a region next to it which is a little bit of lower density, the region which has slightly higher density will have slightly higher gravitational attraction. So that region, which has a high density, will pull matter in from around it. The region which has low density will not attract as much. So what happens is that you want to go from here, this nice universe, to an extremely inhomogeneous universe today. How do you do it? So this is how you do it. These really small overdensities, they have slightly higher gravitational attraction. They attract matter. They become slightly more overdense. Because they're slightly more overdense, they attract more matter. And they become more overdense. And remember, all this is happening over a huge period of time. You have time. The whole point of the universe is that it's 14 billion years old. So you have a lot of time for these small inhomogeneities. Just one part in 10 to the 4 to begin with. You keep building up slowly, get bigger and bigger and bigger, until finally you form a galaxy. So that's the picture that we have. These really small, these tiny inhomogeneities, these little red pieces over here, they slowly attract matter from around them, and they get bigger and bigger and bigger. And each of these red pieces will blow up later in the universe, form a galaxy, or a big galaxy, a supercluster. So these tiny overdensities are expected to grow with time to become today's galaxies, clusters, superclusters, and the regions which had less matter, less energy density at the time of recombination will lose more matter because they have less gravitational attraction. So matter will go away from them, and that will become voids. They will become regions which are empty in the universe. And I'll try to show you that in a minute. But the point is that the way in which these structures grow and the kind of structures that you form you form big structures first, and then they break up and they form small structures? Or you form small structures first, and then they merge and form bigger structures? That is an important probe of cosmology. So if you can measure the size of galaxies at really high redshifts, that's a test of cosmology. It's one of the good tests. So I'll show you a movie now, which will tell you how structures form. So that starts at a redshift of about 20. And this is just the universe. And it's merging under gravity. And so what's happening is it just follows this region over here. So the blue regions are regions which have less mass. The red regions are regions which have more mass. So you can see by redshifts of 1 or so, you already start forming all kinds of stuff over here. That's a picture of how structure forms in the universe under gravitational clustering in the Big Bang cosmology. Let's go through it again. So we're starting about redshifts of 20, and you can see the universe is more or less uniform. This is about 50 megaparsecs, which is huge. The Milky Way is only 30 kiloparsecs in size, so it's about 1,000 times smaller than this distance. And so matter basically flows along these filaments. It's flowing away from these blue regions and flowing into these big overdense regions, and flowing more and more faster and faster as it gets bigger and bigger, until finally you reach this gigantic, big, huge cluster over here. So this object over here is like a supercluster today. It's a cluster of clusters. And that's the picture. So the picture, and we have evidence again for this. When you go out and look at galaxies in the universe, you actually find them sitting in these patterns, these beautiful filamentary structures. They're formed along lines, if you like. And so you actually see things like this, these line-like structures. And this has been known for about roughly 30 years now, since the surveys the first surveys in the 80s showed evidence for this. And so this is the way in which we think structure forms in the universe. It starts from really tiny perturbations in a very homogeneous background, and it slowly builds up just by simple attraction, just because gravity is attractive for normal matter. It slowly adds on more and more and more matter, and the more matter you have, the more the gravitational pull. So it will add more matter. So you keep building up and building up and building up, and then finally you produce these gigantic objects. And the reason this works is that the universe is old. You have 14 billion years in which to do all of this. And that's why you can actually build up really big galaxies. So the first galaxies formed about 500 million years after the Big Bang. So in fact, just about when this thing starts is when the first galaxies form, which is the 20, 25, somewhere about there. We don't quite know this. We actually don't have direct observations at redshifts of 20. That's something that people will do in the next 10 years with this new telescope that's being built, that's being sent to space, the James Webb Space Telescope. You will actually observe for the first time these galaxies, the first galaxies at redshifts of 20 or so. Right now, we know galaxies, we have observations of galaxies, the highest redshift. Over here, we have no observations of galaxies. You can see there are already things forming over here. The first galaxies we know are about here, redshift of 8 or so. So we can actually track the evolution of the universe for sure right now, redshift of 8 down the road. But 10 years down the line, you will actually be able to look at the first galaxy formed in the universe at redshifts of about 20.
我刚刚说这个宇宙学开始有可以证明可以验证，其中一个就是我们可以说一开始看到的这些高低起伏呢，用计算机去算说这些结构密度高的地方引力稍微强一点点，它就容易吸引旁边的旁边的东西，吸引了以后它密度就更高一点，它就更能够吸引旁边的东西，所以这些结构这个反差会越来越大。就能够用这些模拟计算算出到我们现在这个样子，就是我们现在的情形。可是呢，我们现在看到最大的望远镜，我们只能看到这么暗的光线。那么那些光线到我们这边已经太暗了，看不到，我们只能看到这么远，或者是这么久以前的宇宙。再远的光太暗，我们看不到。那现在正在盖天上有一个新的太空望远镜，将来要取代哈勃望远镜的呢。它就可以看到红外线的那个波段比较灵敏呢，它可以看到刚才这个计算一开始的时候 z 等于20，现在大概望远镜大概看到 z 等于8、9大概这样，它可以看到 z 等于20是什么意思呢？就可以看到 更早期宇宙的结构。那些星系发出来的光线，现在我们太阳看不到，以后就可以看到那样的情形，又可以把我们的视野看到更久以前的情形。
That's the picture of galaxies, or the way we think structure formed today. And one of the major areas of research in cosmology today is trying to track the evolution, trying to track how galaxies formed, what are the biggest structures that exist at really high redshifts. So let's move on to the last bit of the talk. And I said that gravity, as we know, is attractive. This thing is completely attractive. See, I have a habit, whenever I give a talk, I always throw something and drop it. Clearly, I managed to do it this time as well. So yeah, so this is, gravity is attractive. So when you drop something up, it falls down, right? So when you throw a bomb up, it goes to slower and slower speed, and then suddenly falls down. It decelerates. Because gravity is attractive, things which are thrown away from a massive object decelerate. And that is because of that an object with some energy, it loses that energy against the gravitational force. And as I said a long time ago, 1 hour ago, what if we throw this thing up and it accelerated away? This would mean that Earth's gravity is repulsive. And this, it turns out, can only happen for bodies made of extremely strange constituents, fundamentally different from matter or radiation. And of course, as with many things in science,